Hello Internet, this video is going to show you how to approximate functions using cubic splines. First, let's talk about some of the ways we can approximate functions. One of them is to just draw straight lines between each point that we have. Another is to draw quadratic lines between each point that we have. Even better is to draw cubic lines. There's another method we can use which gives us an even better looking curve called splines. So what is a cubic spline? It's a function approximation that is continuous at the points that merge, but it also has a continuous first derivative and a continuous second derivative. Let's look at some examples. The first one on the left is an example of two functions that are not continuous. The middle example is two functions that are continuous, but they don't have continuous first derivatives. This last example is continuous as well as having a continuous derivative at the point where they join. A natural cubic spline is still a spline, but it also has a second derivative equal to 0 at the endpoints. And unlike Lagrange polynomials, each point in the line doesn't affect the entire line. So how do you calculate a cubic spline? Well, given a few points, we can write a function for the left 2 points and a function for the right 2 points and set them equal to each other where they join. We also need to make sure that their derivatives are equal to each other and that their second derivatives are equal to each other. And if we're making a natural cubic spline, we also need the second derivatives at the endpoints to be 0. So this is a really large system of equations. Normally, you won't be asked to calculate a cubic spline. Here is an example test problem. Let's say you're given two functions, and you need to find the values of a, b, and c that make this a cubic spline. So let's look at our two functions, and we'll evaluate the first function at the point x equal to 1. Take its derivative, find that value at x equal to 1, and its second derivative, and find that value at x equal to 1. The other equation should have those exact same numbers of -2, 3, and 6. So we'll plug in 1, plug in the 1 at the first derivative, and plug in 1 at the second derivative. This gives us 3 equations and 3 unknowns, which we can solve so that a is 0, b is 0, and c is equal to -3. Let's look at another example. Find the value of a to make this a cubic spline. The first equation is simply s is equal to 0, which is still an equation. We'll also need to find its first derivative and second derivative when x is equal to 1, which is going to be equal to 0. Now let's look at our second equation. We set that equal to 0. Well, that doesn't tell us anything. The first derivative equal to 0 also doesn't tell us much. And the second equal to 0 also doesn't say much. When we say that a can be any value, this is saying that any value of a will make these two equations a cubic spline. But we also want to find the value of a that makes a natural cubic spline. So we'll look at the endpoints. In the first equation, it's going to be 0. But the second equation, the second derivative also has to be 0. And in this case, the only value of a that makes this a natural cubic spline is 0. Thanks for watching.